Good day everyone, this is Module 7, Convolutional Layer Networks. Obviously, this is a continuation of Module 6 where we talked about the multi-layer perceptron or multi-layer neural networks, also known as feed-forward neural networks. So convolutional neural networks, or CNNs for short, are very similar to feed-forward neural networks. They are made up of neurons that have learnable weights and biases. Each neuron receives some inputs, performs a dot product, and optionally follows it with a nonlinearity. Why dot product? So if you remember, the input to this neuron, for example, is the output of this neuron multiplied the weight plus the output of this neuron multiplied this weight plus the bias. So that is actually a dot product between the outputs of this neuron and the weights plus the bias. And nonlinearity refers to the activation function that we have in each neuron. So the whole network still expresses a single differentiable score function from the raw image pixels on one end, for example, to class scores at the other. They still have a loss function. If you remember, error function that we use to compute the performance of our artificial neural network, mean squared error. Sometimes we also use multi-class cross entropy and so on the last fully connected layer. So what does change? CNN architectures make the explicit assumption that the inputs are images, which allows us to encode certain properties into the architecture, even though the conventional feed-forward neural network still would work for input images, but we will see shortly that perhaps it's not that convenient. So recall, feed-forward neural networks, it receives an input, a single vector, and transform it through a series of hidden layers. This is hidden layer 1, hidden layer 2. Each hidden layer is made up of a set of neurons, where each neuron is fully connected to all neurons in the previous layer, where neurons in a single layer completely independently and do not share any connections, which means this neuron is not connected to any of the neurons in the same layer. The last fully connected layer is called the output layer, and in classification settings it represents the class scores. So if you have 10 possible output classes, then you would have 10 output neurons. Feed-forward neural networks do not scale well to full images. Why? In Cipher10. Cipher10 is a database of images. Let's see what is Cipher10. Cipher10 dataset, which stands for Canadian Institute for Advanced Research, is a collection of images that are commonly used to train machine learning and computer vision algorithms. So you can read more about this. Images are only of size 32 times 32 times 3. 32 pixels wide, 32 pixels high, and 3 color channels. A single fully connected neuron, this one for example, in a first hidden layer of a regular neural network would have 32 multiplied 32 multiplied 3, or 3072 weights, because our input neurons would have to be 3072 inputs given our image as such, and therefore a single hidden neuron would have 3072 plus 1 weights. Imagine if you have, obviously we would have more than one hidden neurons, so you can imagine the number of weights that we will require to train. We would almost certainly want to have several such neurons, so the parameters would add up quickly. So CNNs take advantage of the fact that the input consists of images and they constrain the architecture in a more sensible way, where layers of a CNN have neurons arranged in three dimensions: width, height, and depth. In feed-forward neural networks, the neurons are only one-dimensional in a single line. As we will see shortly, in CNN, the neurons in every layer would be three-dimensional. Neurons in a layer will be only connected to a small region of the layer before it, where in feed-forward neural networks, as we saw, each neuron in a layer will be connected to every neuron in the previous layer. For example, this neuron is connected to this neuron, and this neuron. So in convolutional neural networks, we will see shortly that each neuron will be connected to a small number of neurons in the preceding layer. Final output layer would for cipher 10 have dimensions 1 by 1 by 10. So this is similar to what we would have in a feed-forward neural network. But of course, here it will be arranged or depicted as if it's arranged vertically. But given the three-dimensional nature of CNN, we would see that our fully connected layer in the last layer would be horizontal as such. So this is an example of how layers of a CNN would look like. So you can imagine this is our input layer, this is our convolutional layer, perhaps this is our other layers that we will learn shortly. And this is our last layer, 1 by 1 by 10. So you can imagine we have 10 neurons which is laid out horizontally, which is similar to our feed-forward neural networks. And is three-dimensional. So next, three main types of layers to build CNN architectures: convolutional layer, pooling layer, and fully connected layer. And the fully connected layer is exactly as seen in feed-forward neural networks. So a simple CNN for cipher 10 classification would have the architecture input layer, convolutional layer, pooling layer, and fully connected layer. So input layer is simple. It has the dimension as our input images. We'll hold the raw pixel values of the image, in this case an image of width 32 pixel, height 32 pixels, and with 3 color channels RGB. So that's why we have times 3 here. Each channel holds information of one of the color channels, red, green, and blue. So the convolutional layer, as you can see, it has this dimension 32 by 32 by 12. 12 refers to the depth. So this is the depth, right? Computes the output of neurons that are connected to local regions in the input, each computing a dot product between their weights and a small region they are connected to in the input volume. So we will see more detailed explanation shortly on convolutional layer. ReLU stands for rectified linear unit. Each neuron in the convolutional layer applies an element-wise activation function. The equation for the activation function is maximum between 0 and the input. This is how it looks like, the rectified linear activation function. So in each neuron in convolutional layer, we would have the rectified linear activation function. Pooling layer. This is an example of the dimension. And as if you notice, the depth does not change from convolutional layer. So it performs a downsampling operation along the spatial dimensions only, width and height only, and the depth remains the same as compared to the previous convolutional layer. And finally, fully connected layer 1 by 1 by 10. So that is why it is laid out horizontally and not vertically, because the dimensions are 1 by 1 by 10. computes the class scores where each of the 10 numbers correspond to a class score, such as among the 10 categories of cipher 10. So convolutional and the fully connected layers perform transformations that are functions of not only the activations in the input volume, but also of the parameters, where the parameters are weights and biases of the neurons. So the output of convolutional layer and fully connected layer do not only depend on the inputs, but also the weights and biases, obviously, because it has the activation functions in each neuron. Pooling layers will implement a fixed function. It does not have activation functions in it. So this is the architecture of tiny VGGNet. VGGNet is a trained convolutional neural network which you can download from the internet. Each volume of activations along the processing path is shown as a column. The last layer volume holds the scores for each class. So first of all, let's look at the architecture. As you can see, you have convolutional layer with ReLU, with the rectified linear activation functions in it, and it's stacked one after another. So we have convolution, convolution, pooling, convolution, convolution, pooling, convolution, convolution, pooling, and finally fully connected layer. So you can compute how many layers of CNN this is. And when you present the image of a car, you can actually see the activation of each slice of the layers here. And the reason why CNN works well, because each slice of every layer will extract a feature of the image, and the features becomes more and more abstract as we go deeper and deeper. As you can see here, we have images outline of a car, and that outline gets more and more blurred as we go in. And these are called features of the image that we represent. So in the end, the network really classifies the features and not the overall image. So let's talk about convolutional layer. The convolutional layer is the core building block of a convolutional neural network that does most of the computational heavy lifting. For example, suppose that the input volume has size 32 times 32 times 3. So this is 32 width, height, and depth. If the receptive field F is 5 by 5, what it means is that each neuron here will be focusing on 5 by 5 neurons in the preceding layer. Then each neuron in the convolutional layer, this is, like I said earlier, convolutional layer is three-dimensional. It also has width, height, and depth. Each neuron will have weights to a 5 by 5 by 3 region in the input volume, for a total of 75 weights plus 1 bias parameter. So every neuron here will be connected to 75 neurons in the preceding layer. And as usual, dot product will be performed to compute the input to each neuron in the convolutional layer. So in this case, the depth of our convolutional layer is 5. 1, 2, 3, 4, 5. So we would have 5 slices in one convolutional layer in this particular example. 3 hyperparameters control the size of the convolutional layer. The depth, as we saw, this is the depth, stride, and zero padding. So depth refers to number of filters we would like to use, each learning to look for something different in the input. So if we just look at neurons in depth 1, Each neuron in depth 1 will be sharing the same set of weights and bias. And the neurons in the next slice will have different set of weights and bias. So this set of weights and bias is what we call filter. What is stride? Stride is 1 when we move the filters 1 pixel at a time. I think it would be better if I explain by using this diagram. Let's go on the definition first. Zero padding, it'll be convenient to pad the input volume with zeros around the border. So sometimes, given an image, due to some technicalities, we would add 1 pixel of zero value around the images. That is what we call zero padding. It doesn't have to be 1, it depends on the parameter p. So a common setting of the hyperparameters is f equals to 3. This is the field, the receptive field. S is stride, p is zero padding. So let's look at a simple example. So imagine we only have one spatial dimension. So even though CNN is used for images of 2 or 3 dimensions, for discussion purposes, for clarity, let's imagine you only have one dimension of inputs. Our number of input is 1, 2, 3, 4, 5. 5 inputs. So this is our convolutional layer. The depth is only 1. If I had depth equals to 2, then I would have another set of neurons here. 1, 2, 3, 4, 5 here. So in total we would have 10 neurons in our convolutional layer. So we have set the receptive field to be 3. So what that means is that each neuron in the convolutional layer will be connected to 3 neurons in the preceding layer. The input size is 5. Like I said, 1, 2, 3, 4, 5. Zero padding is 1. So we added 1 pixel on each side, but the value is 0. So this is zero padding, we call it. The reason why we add this will be clear in a while. So why do we have 5 neurons in our convolutional layer? It is because, first of all, our field is 3 and stride is 1. So what stride means is that we move this window of 3 1 to the left or right. So imagine 1, 2, 3. If we move to the right, I would get 1, 2, 3. And this become another neuron. And if I move again to the right, so this window will be connected to this inputs now. So that's why we have this neuron in convolutional layer. So if you do the same, if you repeat, you will get 5 neurons because our stride is 1. So stride is, you can imagine moving the window of receptive field. All right. So however, if I use stride to be 2, we only have 3 neurons in our convolutional layer. So this is f equals to 3 because s, the stride equals to 2, we move this 2 times to the right. 1, 2, you have this. And from here, move again 2 times, 1, 2 to the right, you will get this. So the number of neurons in our convolutional layer really depends on receptive field, stride, and zero padding. So notice that stride equals to 3 could not be used since it would not fit neatly across the volume. So if I say my S is 3, stride equals to 3, so this window, if I move 3 times, I would have 1, 2, 3. I would have, this will be covered. This 3 will be connected to 1 neuron. If I move again 3, 1, 2, 3. So I have only one neuron left. So that's why I cannot have S equals to 3. So if I did not have P equals to 1, imagine you only have 5 neurons. Perhaps you cannot achieve any of this. Maybe. Alright. So the neuron weights are in this example 1, 0, minus 1, and its bias is 0. So you can imagine the weights here 1, 0, minus 1, again 1, 0, minus 1, 1, 0, minus 1, and so on. So the weights of every neuron in the convolutional layer in the same depth will be the same, 1, 0, minus 1. And this is different as compared to feed-forward neural networks. Of course, if I had neurons in depth 2, they would be connected to the same neurons, but the set of weights would be different. So how do I get minus 2? So 0, 1, 2 dot product with 1, 0, minus 1, we would get minus 2. How do I get 1? 2 multiply 1 plus minus 1 multiply 0 plus 1 multiply minus 1, I will get 1, and so on. So this is what we call dot product. Of course, in this example, the bias is 0, or else you have to add the bias value. So if we look at a more maybe practical example, this is how the convolutional layer would look like. So imagine this is the preceding layer. In this example, let's take it as input layer. So we have 4 by 4 by 2. So 4 by 4, 1, 2, 3, 4, 1, 2, 3, 4. 2 refers to the depth. So here receptive field is 2. That means each neuron is connected to 2 by 2, but is connected to all the neurons in the depth. So even though it's 2 by 2, this is the window, but it's also connected to 2 by 2 in the next depth or slice. Stride equals to 2, that means this neuron is connected to this 4, 1, 2, 3, 4, this connected to this 4, and this will be connected to 1, 2, 3, 4, 1, 2, 3, 4. Depth equals to 3, that's why we have 3 slices, 1, 2, 3. And again, this neuron will be connected to 1, 2, 3, 4, 5, 6, 7, 8. This neuron will be connected to 1, 2, 3, 4, 5, 6, 7, 8, and with different set of weights. So all the neurons in the same slice will have the same set of weights and biases, and in each neuron we would have the ReLU activation function or rectified linear activation function. And here the padding is 0, so no neurons are added at the sides of the inputs. So the input is 4 by 4 because padding is 0, and this is exactly what we have in the preceding layer. However, if I add P to be 1, we would have to imagine that we have extra pixels around our image or the preceding layer, right? So our input remains 4 by 4 by 2, 1, 2, 3, 4, 1, 2, 3, 4, and 2, but we have 0 pixel added around it. All right, this is added for convenience. If you don't add it with this receptive field and this stride, maybe you cannot achieve the convolutional layer. So here the receptive field is 3. That means each neuron is connected to 3 by 3, but also the next slice. Stride equals to 3 means this neuron is connected to these sets of neurons, because from here you move 3 times, 1, 2, 3, you'll get this 18 neurons. And again, we choose depth to be 3, and that's why you have 3 slices. So what is pooling layer? It is common to periodically insert a pooling layer in between successive convolutional layers in a CNN architecture. Its function is to progressively reduce the spatial size of the representation to reduce the amount of parameters and computation in the network, and hence to also control overfitting. The pooling layer operates independently on every depth slice of the input and resize it spatially using the max operation. It is worth noting that there are only 2 commonly seen variations of the max pooling layer found in practice: a pooling layer with f equals to 3 and s equals to 2 is also called the overlapping pooling, and more commonly f equals to 2 and s equals to 2. So note that in pooling layer we don't have the depth hyperparameter because it will treat each slice independently. For convolutional layer, you have to specify the depth, because each neuron here handles every neuron in every slice. But in pooling layer, every neuron will only handle the neurons in each slice and not every slice. So let's look at this to get some clarity. So imagine this is a layer, a preceding layer. So this will be a convolutional layer, and next we have to do normally the pooling operation or the pooling layer. So because let's read this, pooling layer downsamples the volume spatially. Spatial means height and width, but not depth, independently in each depth slice of the input volume. In this example, this one, the input volume of size 2 to 4 by 2 to 4 by 64 is pooled with filter size 2. So this is the F, the receptive field is 2. So each neuron will be looking at 2 by 2 neurons in every slice. Strike 2 into input volume of size 112, 112 by 64. So the depth is preserved. Notice that the volume depth is preserved. And here is the most common downsampling operation, which is max, giving rise to max pooling, shown with a stride of 2. That is, each max is taken over 4 numbers. So imagine this is a single slice of our convolutional layer. So in this example, we have 64 slices, but pooling would do slice by slice. So looking at the first slice, if our f is 2, that means we will be looking at 2 by 2, and the stride is 2, that means this neuron will be looking at this 2, this neuron will be looking at this 4, sorry, this neuron will be looking at this 4, and this neuron will be looking at this 4. So it's just a matter of taking the maximum. So here the maximum was 6, and this is the output of this neuron. And here the maximum is 8, you have 8. And this is just one slice. We have to do the same for 64 other slices. And that is why here the depth is preserved. So this is different than the convolutional layer, if you remember. In convolutional layer, you have to mention the depth size, right? And every neuron will be connected to the neurons in every slice. But in pooling layer, this neuron will be connected to only this slice. So the most common form of a CNN architecture stacks a few convolutional ReLU layers, follows them with pooling layers and repeats this pattern until the image has been merged spatially to a small size. At some point, it is common to transition to fully connected layers. The last fully connected layer holds the output such as the class scores. So there are several architectures in the field of CNN. LeNet is the first successful application developed by Yann LeCun. AlexNet, we have VGGNet, where its main contribution was in showing that the depth of the network is a critical component for a good performance. Their final best network contains 16 convolutional fully connected layers and appealingly, features an extremely homogeneous architecture that only performs 3 by 3 convolutions and 2 by 2 pooling from the beginning to the end. So this is how the VGG16, the VGGNet 16 would look like. So the one in black, these are the convolutional layer. So in each neuron we would have the rectified linear unit, and the ones in red is the max pooling, the pooling layer. So it's called VGT16 because it has 16 weighted layers. Because pooling layer, it does not have any weight, especially max pooling, because if you remember, we only take the max, right? So from this neuron to this form, there are no weights. You can imagine there are connections, but the operation is just maximum. So VGG16 is named as such because there are 16 weighted layers. So maybe we can try computing it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it's very deep, and it has been shown that it's effective in classifying images. So that's all for this module. I hope you can go along watching this video and ask me questions in our discussion section later.